So I'm going to explain PCA without involving any mathematics. So when we use PCA is simply a dimensional reduction technique. Dimensionality or dimensional reduction technique. So that itself tells something. So what do I mean by that? So dimensional reduction technique means, so I'm sure that you know how to deal with the two-dimensional data. So something like x and y. So let's have some numbers, say a1, a2, a3. Assume these are some numbers, and b1, b2, b3, and b4. So this is really easy to read, for us. For example, we can plot these values x and y, and let's say, so this data belongs to, say, category 1, and the remaining data belongs to category 2. So if you plot this one, you may see something like that. So which means there is some clear separation. You see something which is on one side belongs to category 1, and something on the other side that belongs to category 2. Obviously this is really easy, isn't it? When you are going to deal with a two-dimensional data. And then, even if you don't know that, even if you don't have any information about these first 2 points belongs to one category, and the remaining that sample 3 and sample 4 belongs to category 2, even if you don't have that information, once we plot this data into x and y, you clearly see some two different points. No, so 2 points on one side and another 2 points on the other side. That already tells something, that these 2 points may belong to one category, and these 2 points may belong to another category. So this becomes very simple if you're dealing with only two dimensions, which is x and y. Imagine if you have a third dimension, z. Still we can make such a plot, which may be easy to do in a normal graph paper. And then not a graph paper, maybe using for example Microsoft Excel or MATLAB. Still we can plot a three-dimensional I mean all the data in a three-dimensional axis, isn't it? X, y, and z, and still we can try to visualize the data, isn't it? But in case if you have more than three, then or maybe say you have like, say, 100 columns or something, we can call this one as variables. So if you have multiple variables, variable 1, variable 2, variable 3, variable 4, variable 5. So for example, this can be, say, like you're collecting some information about the students. So this can be their height, this can be their weight, this can be their average mark in one subject, average mark in second subject, average mark in subject that involves heavy mathematics, and so on. So this become some different variables. So in this case, you really have more than three variables, which is really difficult for a human eye to perceive, isn't it? If we have, say, we have the information for 1,000 students, which means you really have enormous amount of data. And if you want to make get any useful information from such a data, one way we can do is we can try to capture all the information in this data, the entire data set, say v1, v2, v3, v4, v5, for, say, like for 100 students. And if you want to capture all the information, the moment I'm not using the right word, but I'm trying to explain the concept of PCA without entering the jargons of PCA. So what we are going to do is we're going to take all the information and then reduce it into two dimensions. So say, for example, let's call that x or y. So we take all the information from the entire data set and then we reduce it into two dimensions. So typically x, this is something called as PC1, which means principal component 1, and y is something called as principal component 2. So this is the whole essence of principal component analysis. So we try to reduce the dimensions of the data into a more readable format, and then these reduced dimensions are typically called as PC1 and PC2. And the word which I use now, information, so the right word in the language of PCA is called variance. So we try to capture most of the information into maybe two or maximum three components. So it's seriously a dimensional reduction technique. So that's why we use principal component analysis, especially we have really a big data with so many variables and we want to extract really useful information from lot of variables into some reduced components. Then so this is the way, this is the algorithm that you actually need. Yeah, so this is a very powerful algorithm. In chemical engineering we use it for a lot of purpose. In chemistry we use it to analyze a lot of information that we get from different analytical equipments. Very very useful algorithm. Yeah, so this is what we are going to learn. And so the easiest way to understand PCA or a principal component analysis is is how do you look at the data, isn't it? Yeah. So for example, imagine if you have a classroom, if you have a lot of students sitting in the classroom, and if you want to capture the face of all the students, so where do you put the camera? So you can put the camera in the front, or maybe in this side, or maybe in this side. It's maybe this side or this side, or even in maybe in the back side. And then we can take a picture of the students. But the best way to capture all the face of the students, maybe you can put a camera somewhere in the top, and then you can ask them to see up, and then you can take a nice picture of them. So what we do is, so that one picture, something we can call it as a principal component one, that get all the information, the facial information about all the students, isn't it? Yeah, so that's how the PCA works. Yeah, so either you can take so many pictures and then assign, okay, this one belongs student 1, student 2, student 3, and student 4, or you take one good picture at the right angle so that you can capture the information about all the students, yeah, with one picture. So that's something we call it as the principal component. So how to do that, or maybe I can still we can try to understand the PCA maybe using a two-dimensional data. Still I'm not entering into the mathematics. So let's say this is some x, maybe the length of the student, and then let's say y, and let's say this is the weight of the students, and let's say we measure the length and the weight of say 100 students, and then if you plot them, so you may assume that we get some cluster here, and we say assume we get some cluster here. So these students, they may belong to uh, the group of students in their age ranging from say like 14 to 16, and this one, let's say the the age ranging from, I don't know, maybe 8 to 9. This is just an example. So so you see that if you plot length and the weight, you already managed to classify two different categories in this type of sample, isn't it? Yeah. So this is the actual real dimension. You actually plot one variable on the x side, which is your length, and another variable on the y side, which is your weight. And now you have a two-dimensional data. Yeah. So in order to make sure that you have two categories in the entire data set. So now we can apply PCA. PCA is an algorithm. So we can apply PCA, and then we can reduce this two dimension into one dimension, and still we can tell that there exist two categories in the data set. Yeah? So, or we can tell there are two group of students. Some group of students age in the range 8 to 9, and other group of students their ages range from 14 to 16. So how to do that? How to do that is, so you need to find the the best component, or something we can call it as the principal component. So whenever I say principal component, let's say I draw a line here. So let's say I draw a line here. Let's call this as PC1, or just let's, for the moment, let's call this as a principal component. And then let's say we try to put a light, and then we project this data, both of this data, one from this side, another from this side. you know, you know, and okay, you don't have to be in the middle, so this can be anywhere in the parallel. Yeah, so for, let's say we put the light somewhere here, sorry, the line here, let's draw a line here, and let's call this as a principal component. At the moment we are not numbering this particular line, and let's say we put a light somewhere on the somewhere here, and then we try to project all the data on this line, dotted line, which we labeled as PC1. So, and what I'm going to do is, so let's say when we project this particular one, all these points that belongs to category 1, you may see some points here, and let's say when we project these points onto this line, so still you can see many overlap, isn't it? You may see 1 point here, 1 point here, 1 point here. Yeah. So clearly there is no separation, and all it says is in this component or in this line, the correct word is component, the once we project the data, they overlap and there is no clear separation, so which means you cannot identify the difference between these two categories. So which means the variance, something we call the right word, the information is not clear, or we can mathematically we can say the variance is very small. Yeah. Variance is very small. And let's repeat the procedure. This time we add a component somewhere here. So I'm going to call this one as a PC1, or the principal component 1. And now let's say if you project, if you put a light here and let's project this one, all these points. Yeah. So which means you're going to carry some information and move that information, and then in this one particular line, which we call it as a principal component 1. So if you project it, so you may get some point here that belongs to category 2. And then if you project these points, this may belongs to, you may get something like here. Yeah. And what does that mean? So what we see here is you have only one single line. Yeah. And that becomes our principal component, and we also see a clear separation between the data points, isn't it? Yeah. So what does that mean? So let's call this as PC1. So if you manage to find this line, and then if you manage to project your data onto that particular line, and if there is a clear separation, so what does that mean? So this line become your principal component, and in this process what we did is we reduced the dimension from 2 dimensions, which is x and y, into one single dimension, and that dimension is nothing but your one of your component, or we can call that as a principal component. So this separation between these two categories will be maximum in the principal component. Yeah. So that's the principal component number 1, or we can say the variance in the data onto that particular principal component is maximum. Pay attention, I'm going to introduce a buzzword now, something related to the PCA. So the direction of this particular line, of this particular principal component, is nothing but your eigenvector. Eigenvector. And then how much information we carry. So if you see clearly a separation between this category 1, category 2, that means we almost captured nearly 100% of the information. That's so what is the 100% of the information? That 100% of the information means there exist the two categories or two group of students in this data. So we roughly captured near to 100% of the information in the data set, but in a single component. And that 100%, or the percentage of the information that we capture, that's something we can get from the value called eigenvalues. So from eigenvalue we can tell how much of information that we can capture in this component, how much of the percentage of information that we capture in this component, so where the information captured is really poor or the variance is very small, isn't it? Yeah? So this is something that we can get from the eigenvalue. So the eigenvalue tells something about the percentage of the information captured. The percentage of the information captured. So this is the the basic understanding that you should have to understand PCA. So the PCA, we will not only reduce the dimension, we do that in a particular fashion. For that, we have to get the direction of this component, which is nothing but your eigenvector, and how much information that we capture in that component, that comes from the corresponding eigenvalue of that eigenvector. So that so if for this type of vector, which is your eigenvector 1, which is nothing but your PC1 or principal component 1, the percentage information that captured on this line, that comes from the eigenvalues that corresponds to this eigenvector. So these are the buzzwords that you have to remember. Yeah. So to summarize, PC is like I already said, dimensionality reduction technique. And then few things that you have to remember is, so if you have two-dimensional data, you can reduce it into one-dimensional data. If you have three-dimensional data, you can reduce it into either two-dimensional or even one-dimensional. If you have multi-dimensional data, say like 10 variables, 10 variables means 10 columns. Yeah, you can reduce it into 3 or 2 or 1. Yeah, so we will come to the rules bit later, but what I'm saying, try to emphasize now at the moment, is how to reduce the data using the so-called principal component analysis. Yeah, and while we reduce, we also try to transfer all the information from the original data set into this reduced number of components. Shortly we call it as PCs, or principal components. Yep. So that should be enough for the moment. And then in the what I'm going to explain is how to read the data itself. Yeah. So how do you define the dimension of the data? I already said dimensionality reduction technique. So let's see, what do I mean by. So if I give you a data, how do you read the data? So um, it's a dimension of the data. So how do you write the dimension of the data? So if I give you some number or some series of columns with so many rows, so the dimension of the data is always rows multiplied by columns. So this becomes the strength, the data strength. How big is your data? So that's something we can explain in the format of rows multiplied by columns. So that's how it works. So for example, you have X and Y, and let's say 1, 2, 3, 4, 5, and then let's measure the corresponding Y value, say 2, 4, 6, 8, and 10. So let's say, so this is, and then let's say sample number 1, 2, 3, 4, 5. So let's say we have some 5 objects, and we are measuring the length, which we label it as X, and then the width of that 5 different objects, and then we try to make a data set, something like that. So if you see this data set, you have what? You have 2 variables. So this is not a variable, this is just a sample reference number. No, so number of samples that we characterized. So we have 2 dimensions, which means you have 2 columns, and then we have 5 samples, that makes 5 rows. So the dimension of this data is row multiplied by column, which means the dimension of the data is 5 multiplied by 2. So that's how you have to write the dimensions of the data. And then something you have to remember, okay, still we are not going into the rules of the PCA, but if you have say like 5 multiplied by 2, so which means you have 5 refers to the number of samples and 2 refers to the, so 5 refers to the number of samples, and this 2 column 5 is the row. No, number of rows usually refers to the number of samples, and 2 number refers to the number of columns. So if you have a data set of 5 multiplied by 2, so you can get 2 PCs. Yeah? So you can get 2 principal components. 2 principal components, But if you want to reduce the number of dimensions, then you can reduce it into one one principal component, one principal component. But this one PC will have nearly almost all the information from the two variables x and y. So now we are going slightly into the rules of the PCA. Yeah. So if we have, say, row multiplied by column, this is the dimensions of our data. So we will get C number of components. So if a data of dimension is 5 multiplied by 3, then we can get up to 3 components. If we have 4 variables, we can get 4 components. If we have 10 variables, then we can, or in other words, you have 10 columns, then you can have 10 components. If you have n variables, say row multiplied by n number of columns, then you will get n number of PCs or principal components. Yes, and if you have to reduce the number of dimensions, then we will which means we can reduce the number of dimension, say from 3 to 2, or maybe 2 to 1, or maybe n to n minus 1, or maybe n to 1 or 2 components. Yeah, so the number of components that we need to capture all the information in the data, irrespective of the number of columns. You may have 1 column, 2 column, 3 column, 4, 5, 6, up say any number of columns. But the number of the game in PCA is you have to identify how many number of PCs that you need, how many number of principal components that you need in order to capture roughly 95% of the information in the original data set, or the mathematical word is 95% of the variance in the data. So this is the main game in the PCA. So you have to identify not only to reduce the dimensions of the data, but you also need to know how many dimensions or number of PCs or principal components that you need in order to capture roughly 95% of the variance in the data. So this is what we are going to do by solving a problem. So what I'm going to do is, I already explained how the PCA works and the purpose of the PCA, which is to reduce the dimension, and then I tell something about how to define the dimension of your data. So that's how we define the data strength and number of PCs that we can get, and how to reduce the number of PCs. And then before, I also showed a few things like so the PCs means you have to find the, so this line, you can call it as a vector, and we can, that vector is nothing but eigenvector. Yeah, so you have to find the eigenvector where you can project your data, and the projected data will carry a lot of information. We have to identify how many number of pieces are required to capture roughly 95% of the information in the entire data set. So here we may capture 100% of the information. Yeah, so you just draw a vector here and you project. You clearly say there exist two different categories, yeah, which mean you capture almost all the information in the data. So that's how the principal component analysis work. So next we will try to solve a small problem, and that's the best way to learn this type of machine learning algorithms. So machine learning algorithms are it may sound very complicated, but at the end of the day, if you know how the algorithm works, then it's really simple. Yeah, the same algorithm that we use to reduce, for example, this type of problem, so x and y, 2 dimension to 1 dimension, is the same algorithm you are going to use to reduce a data set that contains, say, like maybe 100 columns, and maybe like say several thousands of rows. The same algorithm, same number of steps, same rules to reduce the number of dimension, and then we try to capture the information in such a big data into just 2 components. Yeah. So, and note one more thing I forgot to mention. So in PCA, you cannot reduce the number of samples, yeah, because this is something, this, the number of sample means we have a good amount of uh, information from so many materials, isn't it? Yeah? So you cannot reduce the number of rows, but you can reduce the number of columns. So dimensional reduction technique means We capture the information obtained from multiple variables into reduced number of PCs. So that's the meaning of that. Yeah. So we will reduce the number of columns. That's the game in principal component analysis.